This video is related with the book Statistical Modeling with R that I wrote in 2023 and that it was published by Oxford University Press. I'm going to start by a general definition of what is a statistical model, then talk about the issue of parameter estimation, why do we care about it, which is the main goal of statistics, and then talk about a general method used which is the basis of the frequentist the parameter measure in the frequentist framework, which is the maximum likelihood method created by Fisher. Codes and data to run this analysis can be found in the website shown in the screen. So a statistical model is a mathematical relationship between a response explanatory variable y and a numerical and or categorical explanatory variables denoted as x. These in all statistical models, the response variable is a random variable, which means that it has an associated probability distribution that predicts the chances of observing all its possible values. Examples include, in the left, the binomial distribution, where these are counts, model as with a binomial distribution with a parameter p, the probability of success, in this case of the probability of success of 0.38 and 5 observed events. This is the probability of observing 0, 1, 2, 3, 4, and 5. And for the Poisson distribution, these are counts. Here just shown between 0 and 12. It goes to the plus, theoretically speaking, to plus infinity. So these are the probabilities of observing the different counts for when the parameter of the Poisson distribution has a mean of 0.38. And this is likewise the probability of observing different values of the response variable y when this is modeled as if it has a normal distribution with a mean of 20 and a standard deviation of 2.5. 20. Every probability distribution, as we know, is defined by these parameters. That is, once we know the values of these constants, we know or estimate the values of these constants, we can predict the probability of observing every possible value of this response variable y. So there are two main reasons for y to be a random variable, at the very least. One is sampling variability. The values of y that we have in our sample are just a very small subset of all possible values of this variable, in the sense that a second or third or fourth sample we have a different set of values. In order to characterize the variability, the sampling variability across the samples, we use probability distributions. The second is that even when the actual values of y are invariant, but we have successive estimations, but successive estimations yield different values, and the reason for that is measurement error. So we model the uncertainties of the values of y due to the measurement error in the observations using probability. Probability theory is the only existing language that we possess to quantify and interpret this uncertainty in the values of the response variable y. Statistical models postulate a specific relationship between the explanatory variables and the values of the parameters of the probability distributions of the response variable y. For example, let's assume that a given variable, response variable y, has a normal distribution with parameters mean and variance, and we assume that we want to fit a straight line between the response variable and a numerical explanatory variable x. So what we do is that we postulate a linear relationship between the mean of the response variable, the one that has normal distribution, and a linear relationship between the mean and the explanatory variable x. The relationship for any value of x, we would predict an estimated value of y, of the mean of y, and this relationship is governed by the intercept and the slope. We are going to talk about linear regression, which is what this is in incoming videos. The statistical model now becomes that the response variable has a normal distribution with a given mean, but the mean is related to the explanatory variable x,
and this relationship is, as I was saying, governed by the slope and the intercept and the slope of this parameter with a constant variance that reflects the scatter of the values of y around the mean. So this fitted model accounts or explains the variation of the typical values, the values of the highest probability of being observed, those around the mean, of the response variable y. So the goal of statistics is, one of the main goals of statistics is estimating the parameter values along with the precision or standard error that define the relationship between the response and the explanatory variables. So there are three main methods of parameter estimation. The first is the method of least squares that we are not going to discuss here, that was created by Gauss in 1809, estimating the values of parameters only when the response variable has a normal distribution and a few other assumptions. This is the main method of parameter estimation taught in introductory courses. The second is the maximum likelihood, created by Ronald Fisher starting in 1922, and valid for any probability distribution of the response variable y. The maximum likelihood estimates when the response variable has a normal distribution are exactly identical to those obtained by the least square methods developed by Gauss. So in a sense, it makes very little sense to explain the method of least squares for reasons as a general means of estimating parameters, since it has a very restricted applicability. The third method involves are the Bayesian methods, which involve progressive developments based on applying the Bayes rule, and that require algorithms and numerical methods based on Markov chain Monte Carlo. These are going to be explained in the next method, in the next video in this series. So maximum likelihood then. Fisher formulated in 1922 a very general method of parameter estimation for any probability distribution associated with the response variable. His formulation of the maximum likelihood was relatively cryptical. The 1922 paper is a very long, substantial, important, essential, but it's very difficult to gauge where and how Fisher developed the maximum likelihood method. Fisher was a genial mathematician and a very critical writer. A few years later, we actually turned out that Fisher based his maximum likelihood method on the Bayes rule that he firmly rejected, for which he even apologized. So the goal of maximum likelihood is to estimate the values of the parameter or parameters, when there's more than one, that were most likely to have generated observed data given the statistical model proposed for y, given the probability distribution postulated for the response variable y. Bayes rule, discussed in previous videos, becomes the following, becomes the probability of observing the parameter given the data times the probability of observing the data, and that is equal to probability of observing the data given again a set of parameter values times the probability of observing the parameter values. So we will see in the next video, the one devoted to Bayesian parameter estimation, that the second term in the left-hand side is dismissed, and so that the probability of observing the parameters given the data becomes proportional to the product that is in the right-hand side. These three terms have names that we will explain in the video of Bayesian parameter estimation. The one in the left-hand side is called the posterior probability distribution. This is the outcome of the estimation procedure. This is the probability of observing the parameters given the data. The one the first term in the right hand side is called the likelihood, is the probability of observing the data given the parameter values, and the one in the right, the other becomes the prior probability distributions, is the probability distributions of the parameters before we observe the data. So Fisher simply assumed that the likelihood was proportional to the probability of observing the parameters given the data. So therefore the probability, the parameter values obtained by maximizing the likelihood were those that were most likely to have generated observed data given the statistical model for the response variable. So technically speaking, dismissing the prior distribution, which is these probabilities of the parameters, amounted to assume a uniform probability distribution for all parameters. That is, every value of a given parameter theta was equally likely in a given range. So likelihood became the general solution, became a solution to a general problem. Given the data, let's assume counts, and assuming a statistical model, assume that we are going to use the Poisson distribution to model these counts, how can we estimate the value of the parameter, in this case the mean, of the process that could have generated observed data? Fisher defined a function L for likelihood, that depended on the parameter value given the data, instead of the probability of observing the data that could not have been calculated, simply because the data have already occurred. There is no uncertainty about the data. There is uncertainty only about the parameter that could have generated the observed data given the statistical model. So Fisher later on interpreted likelihood as a measure of the rational belief that theta, the parameter of our Poisson model, has a given value given the data and given the model. This is very akin and similar to the epistemic probability that Fisher forcefully rejected all his life. The estimation of the parameter or parameters of the statistical models involves maximizing the likelihood function L, and this could be done very rarely by analytical means, and could be done always by numerical procedures. We are going to illustrate both methods in this video. So let's take an example. Let's assume that we have k abundance counts of an insect, and let's assume that we have the Poisson model as a reasonable model for the response variable y. In this case, the Poisson model has one parameter, the parameter mu, the mean of these counts. Once we know the value of the parameter mu, we can predict the probability of observing each of the possible count values that we have observed. So the probability of having obtained the k count variables is the probability of observing the count lowercase y for the first value, and the probability of observing lowercase 2 for the second value, and the probability of observing the kth count for the k value. And assuming that these k samples were statistically independent, we can simply multiply the probability of this intersection becomes the product of these probabilities, which is what we are stating here by this capital letter pi, and these probabilities are replaced by these Poisson probabilities, by this Poisson model that we are assuming to be correct for the sake of this example. This is the probabilities of obtaining the k data values given the Poisson model and the value of its parameter mu, which is what we want to estimate. So given that the probability of obtaining the data given the parameter value u is proportional to this likelihood, total likelihood, and this total likelihood is the product that we are stating here in the above line. We can replace this total likelihood by this product of these Poisson probabilities for each of the values of our data set. It turns out that it's equivalent and simpler, just for numerical reasons, to maximize the log of the likelihood instead of the likelihood. So we are going to, so the total likelihood becomes the logarithm, the log of the total likelihood is this logarithm transforms these products into a series of sums, which are easier to manipulate on a numerical basis. So, and this is because the log is an increasing and monotonic function, meaning that its derivative, its first derivative doesn't change sign. So the log of the Poisson of the value of mu given the data is maximized for the precisely the same value of mu that maximizes the Poisson, the set of the Poisson probabilities given the data. So what we do is that we replace the formula of the Poisson distribution in the likelihood in order to obtain this, which equals what we have in the right hand side, and applying the properties of the logarithm, this becomes a sum of 3 terms, one of which, this one, does not contain the parameter mu. So what we do then is we try to find the value of mu that maximizes the log of the total likelihood. And this is done in analytical terms by setting its first derivative to 0, as in the same way that we do to maximize any mathematical function. We are trying to find the value of mu that maximizes the log of the total likelihood, and the way to do it is to set this equal to 0. When we set this equals to 0, this allows to have at the end a very simple expression for the parameter mu that maximizes the log of the total likelihood, and that turned out to be the mean of the sampling mean of these counts. So Fisher also proved in that famous paper of 1922 that the second derivative of the log of the likelihood was related to the standard error of the parameter of the estimated parameter, and this turned out to be a generic property of the maximum likelihood estimation, valid for any probability distribution. So besides, in the same paper, also proved that the maximum likelihood estimates were unbiased, consistent, efficient, and they had asymptotically a normal distribution. This allowed Fisher to use the maximum likelihood estimates as part of the inference, or part of the statistical inference and hypothesis testing that he developed in the coming years. So this set of theoretical results and a few others that I am not mentioning here allow Fisher to propose a general method of parameter estimation, a statistical inference, and it must be said that in the overwhelming majority of the cases, maximum likelihood parameter estimation involves very nasty equations that cannot be solved analytically, and so we use numerical methods to find the parameter estimates, the parameter value or values that maximize the log of the total likelihood. So let's do that here. So let's import a data frame in R. These data frames are the counts of the insects. The table here shows that we observe 3 zeros, 5 ones, 15 values counts of 3, 2 counts of 8, and so on and so forth. So we have counts of insects in each of the 50 plants. Let's assume again a Poisson distribution. And so what we can do is to calculate the density of the Poisson distribution for the values that are of the variable of the counts, for each of the counts, assuming that lambda, the value of the Poisson distribution, the parameter of the Poisson distribution, equals 1. Of course, we don't know if this is true, but if this were true, these were the Poisson values. So we can also calculate the logarithm, the log of the Poisson probabilities for each datum, for each of the 50 counts, assuming that the Poisson parameter lambda equals 1, which of course we can sum them up. So we have a single value. This is the sum of the log of the probabilities, Poisson probabilities, for this data set, assuming the Poisson parameter to be equal to 1. So this is actually the expression that we want to maximize, as I explained in the previous slides. So what we are going to do is to write a function in R that can make the same computation for many different possible values of y, the parameter of the Poisson distribution. This is the function that takes an argument lambda, the value of the parameter of the Poisson distribution, and is valid for this data set that we have in this data, for this variable that are the counts that are in this data set. We need now to evaluate the function L Poisson, the one that we just wrote, to calculate the values of the log of the total likelihood for many possible values of y, of lambda, sorry. So we are going to write a data frame, whose variable mean is a sequence starting from point 1, going to 10, separated by values of 0.01. So this is 0.1, 0.11, 0.12, 0.13, up to 10. And then we are going to use the R function sapply to apply the function L Poisson that calculates the log of the Poisson probability, the sum of the log of the log Poisson probabilities for each of the values of these candidate values of the Poisson parameters, and store these values in the L tot value and the L tot variable of the same data frame. Once we do that and we plot the results, we find that for different values of the Poisson parameter, going from 0.1 to 10, we have a given value, a certain value around, say, around here, that maximizes the log of the total likelihood, assuming the Poisson distribution to be the correct model for the response variable. That value turned out to be 13.12, which is the mean of these counts. There are certainly much better and more precise methods than eyeballing the likelihood surface to find the value that maximizes this distribution. But at least this gives you a gist of how this numerical estimation of the maximum likelihood is carried out by software. So in this video, I mentioned what is a statistical model. We extremely quickly discussed the issue of what is the parameter estimation, and discussed and explained an analytical example and a numerical example of maximum likelihood estimation. Thank you for your attention, and I hope you take a look at the next video, which is the one in which I shall explain the method of Bayesian estimation methods. Thank you very much.